Now, is the screen visible?
Yes, sir, it is visible.
Okay. Now, as we have said, we are going to use the incompressible inviscid model of a fluid. So let us look at Euler's equations of motion for an inviscid fluid. Now, this is something you must have come across in your second year course on fluid mechanics. So the vector form one can write as rho times the material derivative of the velocity equal to rho g minus grad p. So here g vector is the gravitational acceleration, p is the fluid pressure, rho is the fluid density, and this vector v is the fluid velocity. Now let us try to give a physical interpretation. If you look at the term rho g, the first term on the right hand side, you know mass times acceleration due to gravity is the weight. So this units of this term will be Newton per meter cube. So each term on the right hand side has the units of Newton per meter cube. So they represent force per unit volume. Now what does force per unit volume mean? To give a proper interpretation, let us consider a fluid particle of volume dV. Now recall that a fluid particle is not a molecule. It is a hypothetical quantity in the continuum model. So you can think of it as consisting of, say, million molecules. But the volume is very small. Now the mass of this particle we can call dm. That will be the local density rho times dV. Now if you take this vector equation and multiply it by dV, then we can write it as rho dV multiplied by the material derivative of the velocity equal to rho dV times the gravitational acceleration plus minus grad p multiplied by dV. Now recognizing that rho dV is dm, the same equation I can write as dm times the acceleration of the particle, which is the material derivative of the velocity, equal to dm times g plus this quantity minus grad p dV. Now the left hand side of this equation is the rate of change of momentum of the fluid particle. So it is the mass times the acceleration of the particle. So this is nothing but Newton's law. So you have to recognize what are the forces on the fluid particle. The first term is easy to recognize. It is the gravitational body force acting on the fluid particle. The second term on the right hand side is the net surface force on the fluid particle due to pressure exerted by the fluid surrounding the particle. So what we are calling a fluid particle is just a small chunk of fluid which is surrounded by fluid on all sides, and the surrounding fluid will exert a force on this chunk of fluid that we are calling the fluid particle. So by looking at this equation now, we can argue that the net surface force on a fluid particle exerted by the surrounding fluid when it's inviscid is, I'm calling it the vector F with the subscript pressure, and I put a parenthesis and written net equal to minus grad P into dV. Now what are the units of pressure? It is Newton per meter square, and grad has a del del x, del del y, del del z. So grad P has units of Newton per meter cube. If you multiply it by the volume, then it is Newton. The units will be Newton per meter cube multiplied by meter cube. So the SI units will be newtons. So what you can see from here, this expression is that suppose the pressure does not vary from point to point, then the net force on the particle due to pressure will be 0. So there is a net force due to pressure on a particle only when the pressure field is varying spatially, so that the pressure at different points on the surface of the particle is different. Otherwise, there is a cancellation effect and the net will be 0. So this is an important concept that we need to do. So what we have found is the net force on an particle of infinitesimal volume. It is simply minus grad P multiplied by dV. Now, while talking about the Bernoulli head, the Bernoulli function and head, I've already introduced this term which we are referring to as piezometric pressure. Some people call it modified pressure. So here I have denoted it by P with the superscript star. So this is small p minus the density into this quantity G dot R. R is the position vector of a point. So the first term on the right hand side, the P, sometimes you may call it static pressure. Okay. And the left hand side is the piezometric pressure. Now I'm leaving this as an exercise, but you can show that grad of P star, grad is a linear operator, so it will be grad P minus grad of rho G dot R. And this you can write as rho G minus grad rho into G dot R. Okay. So as an exercise, you can consider a function which I've called chi, which is G dot R. So if you write it in component form using Cartesian coordinates, G dot R will be the sum of 3 terms. The first term is Gx times x, the second term is Gy times y, and the third term is Gz times z. So here Gx, Gy and Gz are the x, y and z components of the vector G, the gravitational acceleration. So this will depend on your choice of coordinate system. So suppose you choose a coordinate system where the z-axis is vertical and the xy plane is the horizontal plane. In that case, Gx and Gy will be 0. So the first 2 terms will be 0. And the next term will be minus G if z points upwards. And it will be plus G if z is vertical but points downwards. So the choice of the coordinate system is up to you. Now you can always take an arbitrary coordinate system with the axis oriented at arbitrary angles to the vertical. In that case, Gx, Gy, Gz will depend on your choice of the orientation of the axis. Whatever it is, G dot R, this whole quantity, the sum of these 3 quantities, is invariant under coordinate transformation. So the sum of the 3 terms will have the same value irrespective of the coordinate system that you may use. Now as an exercise, you can first find what is the partial derivative of this function chi with respect to x. Now can anyone tell me quickly what is the value of this?
Gx, G of x,
G subscript x. What about part B? The partial derivative of chi with respect to y?
G of
Gy.
y.
Okay, and the part C, del del z of chi?
Gz.
Gz. Okay, so the partial derivative of chi with respect to x, you expect it to be gx. And if I replace x by y, we get gy, and if we replace y by z, we get gz. So what will be this vector grad of chi?
G vector.
G
It will be the
vector.
g vector. Okay. So if you look at grad of this whole quantity rho g dot r and allow rho to vary with space, then you have 2 terms. One involves grad rho times g dot r. Other term will be rho grad of g dot r, which is grad of chi, and that is simply your g. Now, we'll be dealing with an ideal fluid. So we'll assume that the density is constant. That's a good assumption in case the fluid is a liquid. So if rho is constant, then grad rho will be 0. Okay. So there'll be only two terms on the right hand side of this equation, grad of P star. Okay. So grad of P star then will be simply grad P minus rho G. Now if you go back and look at the Euler's equations of motion, the right hand side, left hand side is the mass times the acceleration per unit volume. Right hand side are terms which have units of force per unit volume. So you have rho G minus grad P, which you can then recognize as minus of grad P star. So we can rewrite Euler's equations of motion as the density rho multiplied by the acceleration, which is the material derivative of the velocity, equal to minus grad of P star. So this term, grad of P star, includes the net force due to pressure as well as the gravitational body force. Now if we go back and look at the vector form of the equation, okay, you see on the left hand side one term, but this actually stands for a group of 4 terms. Similarly, the last term is actually the sum of 3 terms. Okay, but I grouped them together because they have a physical meaning. Okay, so in this equation, the first equation that I've shown you today, there are 3 terms, one on the left hand side of the equation and 2 on the right hand side. Now these 2 terms on the right hand side, now we are able to combine and write as one term minus grad of P star. Of course, this you can do only when the density is constant. If the density is not constant, then you have to subtract off this term, grad rho into G dot R. So there's no advantage of doing it, advantage in doing this when rho is varying with the spatial coordinates. But when rho is a constant, you see that 2 terms on the right hand side have been lumped together as one term. So you have to deal with one less term in the equation. Now, of course, the derivative capital D dt we can think of as the Lagrangian time derivative. That is following the fluid particle. Yeah, any questions? Does somebody have a question? Okay, now we can write the material derivative of the velocity as the temporal derivative del v del t plus the convective term v dot grad v. So this del v del t, this partial derivative, you can think of as the Eulerian time derivative. So it is the rate of change of the velocity as measured at a given point. And on the equation, in the equation preceding this d dt is the rate of change of the velocity of a particle which is moving from one point to another point. Now we would like to write Euler's equations of motion in streamline coordinates. Now you may recall that yesterday I had introduced to you the equation of a streamline. So if we can describe the equation of a streamline in various forms, one convenient form is to use this parametric equation, position vector r equal to r of s, where rs is the position vector of a point on the streamline and s is the arc length along the streamline measured from a convenient reference point. So if I say E subscript s is the unit vector tangent to the streamline, then as I've shown you yesterday, Es will be dds of the position vector r, provided s is the arc length. And so this holds for any curve, okay? But if this curve is a streamline, then ES must be in the direction of the velocity vector V. Now since ES is a unit vector, we can write it as the vector V divided by its magnitude, which I'm denoting by this symbol capital V. So capital V is the absolute value of, or the magnitude of the vector V. You can think of it as being the square root of V dot V, the scalar product of V with itself. So here we have taken the plus sign here. One can also have another unit vector which is tangent to the streamline but pointing in the opposite direction. So if you take the plus sign, then ES is pointing in the direction of the velocity vector. So it gives you an idea of which way the particle will move if it's a steady flow. Now, since ES is a unit vector, the dot product of ES with itself will be 1, because this is the square of the magnitude of ES. Now this relation holds for all values of this arc length parameter S as you move along a streamline, and hence one can differentiate each side of this equation with respect to S. So this will give you del del S of ES dot ES equal to del del S of this constant 1, which is obviously 0. Now del del S of ES dot ES will be twice ES dot del ES del S. So you must have seen a relation like this in your course on engineering mechanics in your first year. So if we take this relation and substitute over here, you will get twice ES dot del ES del S equal to 0. Or in other words, we can drop the 2 because the right hand side is 0. We have an important relation that the scalar product or the dot product of the vector unit vector ES with its derivative in the streamwise direction ES dot del del S of ES is a scalar quantity which is 0. Now when can the dot product or scalar product of two vectors be equal to 0?
When they are
Perpendicular.
perpendicular. When they are perpendicular.
If both the vectors are non-zero, then they have to be orthogonal. The angle between them must be 90 degrees. Or you could have a case where one is a 0 vector or null vector. Now ES is not a null vector. It has magnitude 1, but we don't know about del ES del S. So there are two possibilities. Either del del S of ES is a 0 vector, or in case del del S of ES is not equal to 0, then the vector del ES del S must be orthogonal to ES. Now note that in the first equation that you see on the screen, the 0 on the right hand side is a scalar 0, because the left hand side is a scalar quantity. It is the scalar product of two vectors. Now if you look at the second equation on the screen, the left hand side is a vector. Okay, so if I write the right hand side as a scalar 0, that is not acceptable. That will be an error. So I've written it in boldface. So this dark 0 means it is 0 EX plus 0 EY plus 0 EZ. It is a 0 vector, or you can call it the null vector. Alright. Now let us look at the first case where del ES del S equal to 0. So you can give a geometric interpretation. If you move along a streamline and you find that the tangent vector is not changing with S, that means they are parallel vectors. So that will happen when the streamlines are straight lines, or you can say the streamlines are rectilinear. Okay. So in this sketch, I've shown 2 points, 1 and 2 on a given streamline, which is a straight line. And at point 1, the unit vector I'm calling ES1 with a hat. So this hat sign or caret symbol, it denotes an unit vector. The magnitude is 1. Now at point 2, I'm showing another arrow and I'm calling it ES subscript 2 again with the caret sign or hat sign. So again its magnitude is 1, but if the two are equal, then they are parallel vectors. Okay. Now likewise, I've taken another streamline and I've taken 2 points. I've called them 3 and 4, and you see that here ES subscript 3 and ES subscript 4 both point in the same direction and both have unit magnitude. So as you move from 3 to 4, that is as S increases from S equal to S3 to S equal to S4, ES does not change. So del ES del S is 0. Similarly, if you move from point 1 to point 2, the value of S is increasing from S equal to S1 to S equal to S2. It does not change. So this is a trivial case. All right. Now, let us look at a non-trivial case where the streamlines are curved. So if the streamlines are curved, it means that when you're moving along the streamline from one point to the next, the unit vector tangent to it will change. Of course, its magnitude will remain 1, but it will point in different directions, which means that the streamline will not be a straight line. Okay. So I've shown you a figure. This blue line is, let us say, a streamline. And I've considered a point here, and I've shown the unit vector tangent to it, which I'm calling ES. And I've drawn a vector which is normal to this. I've called it E subscript n. And I've taken the vector which is pointing towards the center of curvature. So of course, this streamline may not be a circular streamline, but you can locally always define a center of curvature. All right. So I've shown constant vectors Ex and Ey at the center of curvature. Okay. And I've taken a reference line here, which is parallel to the OY axis. Okay. And to fix ideas, I've defined an angle which I'm calling phi, which is measured from this line. Okay. Now, you can see that if I draw the horizontal and vertical lines at the point here P, where I'm placing the cursor, this is the point on the streamline. You see that if I say the x-axis is horizontal and the y-axis is vertical, then this unit vector ES is inclined at a direction, angle of phi. Yeah, any questions? So this unit vector ES is inclined at an angle of phi from the vertical, horizontal, whereas the unit vector En is inclined at an angle of phi from the vertical. So I can express this unit vector ES as a linear combination of the constant unit vectors Ex and Ey. Okay, you can call them I and J perhaps, but in this course I'm referring to them as E subscript X and E subscript Y. Okay. So if this vector has unit magnitude, its X component will be cos of phi and the Y component will be sine of phi. So you have ES is cos phi EX plus sine phi EY. And if you look at the magnitude of ES, it will be square root of cos square phi plus sine square phi, which is 1. So according to the direction shown in this figure, ES has a component in the plus X direction and the plus Y direction. Okay. So it has a positive X component and a positive Y component. But this vector En, it has a positive Y component but the x component is negative, the way this figure is drawn. Okay. Now, if the magnitude of En is 1, if you drop a perpendicular here, then the y component will be cos of phi, and the x component will be sine of phi. So En then is minus of sine phi times Ex plus cosine phi times Ey. So once again, if you want to find out what is the magnitude of En, it will be square root of the x component squared plus the y component squared. So it will be square root of minus sine phi whole square plus cos phi whole square, which again is 1. Now, if I move from one point to the other point, the direction, the magnitude of Ex and En will remain the same. In all cases, it's 1, but they'll point in different directions. And this angle phi will also change because the streamline is curved. So let us find out the rate of change of Es with phi. So you can differentiate this equation, and noting that Ex and Ey are constant vectors, the derivative then will be derivative of cos phi is minus sine phi, and the derivative of sine phi is cos phi. So you see that it's easy to see that dd phi of Es is minus sine phi Ex plus cos phi Ey, and if you compare this term, this quantity minus sine phi Ex plus cos phi Ex with En, you see that this is equal to En. So you can give a geometric interpretation. If you take the derivative of Es with respect to phi, you are getting a unit vector which is rotated 90-degree anti-clockwise from Es. Okay. And as an exercise, you can see that if you take the derivative of En with respect to phi, it will be minus Es. So again, this vector will be rotated 90-degree anti-clockwise. So taking the derivative with respect to phi of these unit vectors, this operation will produce a vector, another unit vector, which is at right angles to the original vector and rotated 90-degree in the anti-clockwise direction or counterclockwise direction. Okay, now we would like to find out how Es varies with S. So using the chain rule, you can say del del S of Es is dd phi of Es into del phi del S, and dd phi of Es we have seen is En. So this is a vector which is in the direction of En, and its magnitude is del phi del S. Okay. So this is something we had already concluded. If you go back and look at this, we have said that since Es dot del del S of Es is 0, if the vector del del S of Es is not a 0 vector, then it must be perpendicular to Es. And in this figure, we have shown the direction En perpendicular to Es. Now, of course, minus En is also a vector, unit vector, which is perpendicular to Es. Okay, so it's important to look at what is the direction of what we are calling En. Okay, so En is a unit vector perpendicular to the unit tangent vector Es and pointing towards the local center of curvature. So you get this relation that this derivative of Es, del del S of Es, is a vector which points in the direction of En with the value of this del phi del S. Now let us take a special case. Suppose you have a case where the streamline is a circle. Then the arc length S I can write as the radius R of the circle multiplied by the angle in radians, which I am calling phi, from some reference radial line. So go back to this figure and assume now that this is a perfect circle. Okay. Then S will be R phi, and it's clear that ds d phi will be R. Phi is dimensionless, so S and R have the same units of length. So the SI units will be meters. And if you look at d phi ds, that will be the reciprocal of R, 1 upon R, which is the curvature of the curve. So for this case of a circular streamline, this del phi del s I can replace by 1 by r. So del s of Es is 1 upon r times En. In general, of course, you may have a curved streamline which is not a circular streamline. You can call this quantity del phi del s, you can identify it as the curvature of the streamline, and the reciprocal of this curvature you can say is the local radius of curvature, r. So the term that is important here is local. So we can write del s of Es as the curvature kappa multiplied by En, or as 1 upon the local radius of curvature multiplied by the vector which we are calling En. So En is a unit vector normal to Es and points in the direction of the local center of curvature. Now we define a quantity vector which you might have studied in your dynamics course. We'll call it the principal normal vector. So we have seen that En and del s of En point in the same direction. Okay, but del s of Es is not a unit vector. But if we divide del s of Es by its magnitude, then it will be a unit vector. So this quantity that we have labeled as En in the figure is referred to as the principal normal vector. It is a unit vector and it points in the towards the local center of curvature, and it is going to be orthogonal to the unit tangent vector Es. So I have summarized it here, this information. The unit vector E subscript n points towards the local center of curvature of the streamline. So the key word here is local. Now we can define another vector which we'll call the binormal vector, which is the cross product of Es and En. So you know that the cross product of two vectors is a vector which is perpendicular to the plane containing these two vectors. So EB vector is a vector which is normal to the plane containing Es and En. Do you know what this plane is called from your knowledge of dynamics? Have you come across this? Have you heard this term oscillating plane?
No, sir.
Okay. Anyway, it's not important. Now these are Es and En are unit vectors, so the cross product will also be a vector which has unit magnitude. Okay. Now I've shown this the three vectors on another sketch. So suppose you have a streamline which I have indicated by this blue curve. Okay, and I put an arrow to show the direction in which the particles will tend to move. Okay, it's the direction of the flow. So at this point here, I'm putting the cursor here. You can call it point P on the streamline. I've shown the three unit vectors. One is tangent to the curve, the unit tangent vector, which we are calling Es. So S is the arc length along the streamline, and Es is a vector tangent to the streamline. So this Es is in the direction of the velocity vector at this point, and En is the what we are calling the principal normal. It points towards the center of curvature of the streamline, and EB is another vector which is normal to Es. So there are two vectors, En and EB, both of which are normal to the vector Es. So En and EB form a plane, and Es is a vector which is normal to that plane. So this third vector, which we are calling EB, is another unit vector. We are calling it the binormal vector. So the subscript B is to remind you that this is the binormal vector. And the subscript N here tells you it is the principal normal, just normal. And these hat signs or caret signs remind you that these are unit vectors. Now, of course, when I've typed the vectors. I'm not putting the caret sign and the hat sign. I'm simply putting it in bold. Okay. But you understand from the context that all the vectors which we are calling E with any subscript, these are unit vectors. Now, ES, EN and EB, they form a right-handed coordinate system locally. Okay. So ES cross EN is EB, the way we have drawn it. So look at this triad of unit vectors, ES, EN and EB. They're all mutually orthogonal. Okay. And they're unit vectors. So they form an orthonormal basis just like your EX, EY and EZ. So if you look at the scalar product of ES with EN, this is 0 because the angle between ES and EN is 90 degree. Similarly, EN dot EB is 0 again because the angle between EN and EB is 90 degree. And EB dot ES is also 0 because the angle between EB and ES is 90 degree. And if you look at the scalar product of ES with itself, that is the square of the magnitude of ES, that is 1 because it's a unit vector. And EN also is a unit vector, so EN dot EN is 1. And the way we have defined EB is the cross product of two unit vectors. Okay, so you can show that EB dot EB is also 1 because the magnitude is 1. Now what you can do is consider a curvilinear orthogonal coordinate system, which we will refer to as S, N and V. So S is a streamline, is the arc length along a streamline, and N locally, if I go back to this figure, is distance normal to the streamline in the direction of En, and V is distance normal to both En and Es in the direction of Eb. Now the grad operator you can express in streamline coordinates. So this S, N and V will call streamline coordinates. So it will be ES del del S plus En del del N plus EB del del B. Now we have come across this term grad of P star, where P star is the piezometric pressure. Then I can write it in this basis, okay, as del del S of P star ES plus del del N of P star En plus del del B of P star times EB. Now likewise, let us look at V dot grad V, which is referred to as a convective acceleration. Now the vector V we can write as this magnitude, the scalar capital V multiplied by the unit vector ES in the direction of the streamline, tangent to the streamline. So this is the unit vector in the direction of the velocity vector. So V ES dot grad V. Now ES dot grad is the directional derivative del del S. So one can write V dot grad V as the scalar V into del del S of the vector V. Okay. So the easiest way to think of it this way is that V dot grad is a scalar operator. Okay. So this is something you might have come across in your second year course on fluid mechanics. Now if you know that grad of a scalar is a vector, so grad V is a vector. So you may ask, what is grad of a vector? Well, that is a tensor of rank 2, or you can call it a dyad. Okay. But anyway, let us not worry about all this. This is not a course on fluid mechanics. We just want to move on and get some key results which will help us predict the performance of turbo machines. But I'm trying to develop the course material logically from first principles. So I'm going through all this review. So V dot grad V is a vector which is called the convective acceleration. It is the scalar capital V, the magnitude of the velocity, into another vector which is del del S of V. Now what is del del S of V? I can write it as del del S of capital V into ES. So it is a derivative of a product, so there will be two terms. the first term is the derivative of the first function del v del s into es, and the second term will be v times del es del s. Now del es del s we know is in the direction, is a vector which is not a unit vector, but it points in the direction of en, and its magnitude is kappa. So del del s of the vector v is del del s of the scalar v into es plus the speed of the fluid capital V into the curvature times en. So this is a vector which has a component in the direction of es as well as en. Notice that there is no eb component here. So if I multiply this by this speed, fluid speed, then I get the convective acceleration. So this happens to be v del del s of v. So this is a scalar multiplied by es plus v square into kappa into en. Okay. Now the first term we can interpret as the tangential acceleration due to the change in the speed of the fluid particle as it moves along the streamline. And the second term you can view as the centripetal acceleration, because en points towards the center of curvature, and this kappa is like 1 upon r. So this is like v squared by r. So v dot grad v, the convective acceleration. So this is acceleration because of spatial variations of the velocity field. We can write as the tangential acceleration plus the centripetal acceleration. So the tangential acceleration is magnitude is the speed v multiplied by the rate at which the speed is changing with the arc length coordinate along the streamline. And the centripetal term is the curvature multiplied by the square of the velocity. Now let us use this and substitute this expression here, this entire expression, and this expression into Euler's equations of motion. Which we could write as the temporal acceleration term, rho times the temporal acceleration plus rho times the convective acceleration equal to the minus grad of p star. Now let us not worry about the first term, the temporal acceleration or the Eulerian derivative of the velocity. Later on we'll be looking at steady flows where this term is 0. Okay. Now we have been able to express the convective acceleration in streamline coordinates, and we have an expression for grad p also in streamline coordinates. Okay. So armed with this knowledge now, we can write the equations in a form which you can interpret physically. Okay. So I can write it as the density rho times the sum of 3 terms. The first term is what we call the temporal acceleration. This is the local rate of change of velocity at a given point. So it is not the acceleration of a particle. But if you add the other 2 terms to it, then you get the acceleration of a particle. So other 2 terms are the tangential component of the acceleration and the normal component of the acceleration, centripetal acceleration. As we have seen, there is no term involving EB in the convective acceleration. On the right hand side, we'll have 3 terms here. Now we can equate, so this is a vector equation. Any vector equation is equivalent to 3 scalar equations. So what you can do is look at the ES, the coefficient of ES on either side of the equation and equate them. Then you can look at the coefficient of En on either side, and you can look at the coefficient of EB on either side. Okay. So that's easy to find when del V del T is 0. Okay. So when del V del T is 0, on the left hand side you have only rho V del V del S. Okay. So if you look at Euler's equations of motion for steady flow of a constant density inviscid fluid, if you equate the coefficient of ES, on the right hand side you have minus del S of P star, and the left hand side you have rho V del V del S. And if you look at the coefficient of EB, the left hand side, if it's steady, this term is, suppose the first term here is 0, then left hand side will be 0. And if you equate the coefficient of En, you will have minus del P del N the right hand side and kappa V square term the left hand side. Okay. Now, it's not easy to express del V del T as a linear combination of ES, EB and EZ. But another way to get this equation is, if you want the S momentum equation, that is the component of this vector equation in the direction of ES, then another way to get it is take the scalar product of each side with ES. Okay. And if you look at the right hand side, ES dot ES is 1, so we get minus del P del S. Okay. But ES dot EN is 0 and ES dot EB is 0, so these two terms vanish when you take the scalar product. Similarly, if I look at the left hand side and take the scalar product with ES, the last term vanishes because ES and EN are normal to each other. And ES dot ES is 1, so we get rho V del V del S, the tangential acceleration term, convective acceleration. And the other term I can write as rho ES dot del V del T. Similarly, if you look at, if you want the component of this vector equation in the direction of En, okay, the normal component or the n momentum equation, we can look at each side of this equation and take the scalar product with En. Now first look at the right hand side because that's easy. En dot En is 1, so you get minus del del n of P star. But En dot ES is 0 and En dot EB is 0, so you don't get anything on the any contribution from the other two terms. Now if you look at the left hand side, En dot En is 1, so we have this term rho kappa V square. And this term vanishes because En dot ES is 0, and the unsteady term here I can write as rho En dot del V del T. And likewise, if you want the component of this vector equation in the direction of the unit vector EB, you take the scalar product of each side of this vector equation with EB. The right hand side simply reduces to minus del del V of P star. Okay. On the left hand side, the second two terms will be 0, and you have just the unsteady term EB dot del V del T. So these three equations are Euler's equations of motion in streamline coordinates for a constant density in viscid fluid. But I have not yet imposed the restriction of steadiness. This is valid for unsteady flows. But we'll be dealing in this course mainly with steady flows. So when the flow is steady, this temporal acceleration is 0. But of course, the material derivative is not 0. So capital D dt of V is not 0, but del del T of V is 0 if the flow is steady. That means the velocity at a given point is not changing with time. But if you move from one point to another, there may be a spatial variation. So when a particle is moving along a path line, it can move into a region with a different velocity, and there will be an acceleration which you call the convective acceleration, even when the flow is steady. So when the flow is steady, the first terms on the left hand side of these three equations will be 0, and they simply become rho V del V del S equal to minus del del S of P star, rho kappa V square equal to minus del del N of P star, and the other one is 0 equal to minus del del V of P star. So I've dropped the minus sign and simply written it as del del V of P star. So what this tells you is that the piezometric pressure will not vary in the direction of the unit vector EB, the binormal vector. So P star will vary in general along the streamline in the direction tangent to the streamline and in the direction normal to the streamline. Okay. So we have come to the end of 55 minutes. We can have a short 5-minute break, and then we can try and integrate this equation along a streamline. So next we'll look at integration of Euler's equations of motion along a streamline. What's the case when the flow is steady and inviscid, the density is constant, and the gravitational force field is gravity vector is constant. Okay. And this will give you a scalar equation, which we call the Bernoulli equation. Of course, the Bernoulli equation has many forms. We are looking at the form for steady constant density flow. Okay. Now, do you have any questions regarding the material that we have covered? So what we have done is looked at Euler's equation of motion for steady flow along in streamline coordinates, and this will tell us how pressure varies in the direction normal to the streamlines. This will help you find forces on vanes. At least it will help you visualize in which direction the net force due to pressure will be. And it will also give you Bernoulli's equation. Any questions?
No, sir. No. Sir, so do we have a break now? 5 minutes. Hello?
Hello? Do you have a question? All right. So let us start again. We'll start with the S1. So we can, I've written here 3 equations. So the keywords here are steady flow, constant density fluid, inviscid fluid. Okay, and of course, since I've used this piezometric pressure here in this form, we have also assumed that the gravitational acceleration is constant. But usually the gravitational acceleration is constant for all the cases that we will consider in this course. So that is not a restrictive assumption. Okay. And since we are dealing with hydraulic machines, the fluid is water, so constant density is a good approximation. Okay. So the key things are, we are assuming the flow to be steady. Now, we'll see later on that the flow may be, whether the flow is steady or not will depend on the frame of reference. So we'll be dealing with a stationary frame of reference and a moving frame of reference. So first I am dealing with flow which is steady in a stationary frame of reference. Then we'll generalize it to cases where the flow may be unsteady in a stationary frame of reference, but steady in a translating frame of reference. Okay, so these are important concepts, and we are neglecting viscous effects because otherwise you cannot get a simple analysis. Okay, so you have the momentum balance in the S direction or direction tangent to the streamline, the N direction or the direction normal to the streamline, and the third direction which is also normal to the streamline. So the middle equation here is the momentum balance in the direction of the what we are calling the principal normal, and the third equation is the momentum balance in the direction of the binormal. Now let us focus our attention on the S momentum equation. When the flow is steady and inviscid and density is constant, we can write it as the density rho times the tangential acceleration, which is the speed capital V multiplied by del del S of V. So this term will be 0 if the speed does not change with S. Excuse me. In that case, you will only have the centripetal acceleration due to the change in direction of the velocity vector. But this is a general case. The speed can also change in the direction of S. So I have only one term on the left hand side and one term on the right hand side, and both are derivatives with respect to S. Now V del V del S one can write as del del S of V square by 2. So if you are asked to find del del S of V square by 2, you use the chain rule, write it as ddV of V square by 2 into del V del S. And ddV of the V square by 2 is simply V. So on the left hand side, the acceleration term one can write as rho times del del S of V square by 2. Now in case the rho is constant, this quantity can be moved inside the derivative, and I can write it as del del S of rho V square by 2. And I can take the term on the right hand side and transpose it to the left hand side and write this equation as the sum of two terms equal to 0. And since del del S is a linear operator, I can club these two terms together and write it as del del S of this sum, which is P star plus half rho V square. So if I look at the sum of these two terms, which I am calling the sum of the piezometric pressure and the kinetic energy per unit volume, half rho V square, this quantity will not vary in the direction of S. If the flow is steady and inviscid and the density is constant. Now P star itself is the piezometric pressure, which is P minus rho G dot R. P is a static pressure. So we can, although I have written this as two terms, sum of two terms, it is actually the sum of three groups of terms. Now once again, G dot R may be one term if the coordinate system is vertical. One of the coordinate axis is vertical. Otherwise, in general, this stands for a group of 3 terms. And v dot v also you can write as a sum of 3 terms. So v dot v is square of vx plus square of vy plus square of vz. So this is a vector invariant form, del del s of p minus rho g dot r plus half rho v dot v equal to 0. So if I define what I've done before, if I denote the sum of these 3 terms by a function which I call capital V, then this momentum equation in the tangential direction we can simply write as del del s of capital V equal to 0. So this equation is equivalent to this equation, okay, written in a disguised form. So if del del s of V is 0, then V does not vary with S. So it means that this function V is a constant along a streamline. When the flow is steady, inviscid, and the density is constant, and the gravity field, the gravitational acceleration is also constant. So this equation, as you know, is called Bernoulli's equation. So this function I have denoted by capital V so that it reminds you about Bernoulli's equation. So we can call it the Bernoulli function. So V itself is a function of x, y, z. Okay, it's not a function of t because we are looking at steady flow, but it can vary from point to point in general. But if you take 2 points on the same streamline, the value of V will be the same. But if you take 2 points on different streamlines, the numerical values will be different. So the numerical value of the Bernoulli function V may vary from one streamline to the next. Now, let us look at the variation of the piezometric pressure in a direction which is normal to the streamlines. So we'll look at the component of Euler's equations of motion in the direction of the unit vector En. So as we have seen, we can write it in this form: del del n of P star equal to minus of the density rho multiplied by kappa, the curvature, times the square of the speed. And if you think of it that way, I can write kappa as 1 upon the local radius of curvature. So this quantity kappa times v square is v square by r, which is your centripetal acceleration magnitude. Okay. So what this equation tells you is that this quantity del del n of P star is negative. Why? Because density is positive, v square is positive, and kappa is 1 upon r. The way we have defined it, it is the magnitude of del del s of Es, so that's also positive. So what does it mean? It means that if n increases, then P will decrease. Now, when will n increase? Well, you have to look at the direction of the unit vector En. It points towards the local center of curvature. So if you wish, I can go back to the figure which shows the streamline. En is pointing towards the local center of curvature, which is here. So n will increase as you move towards the local, move in a direction normal to Es and towards the center of curvature. So as n increases, what will happen? P star will decrease. That means P star is larger when you move out away from the center of curvature, and P star will decrease as you move towards the center of curvature. So n, the value of the coordinate n, will increase when one moves in a direction normal to the streamlines, to be more precise, in the direction of the unit vector n towards the local center of curvature. Or conversely, you can say that if you move in a direction normal to the streamlines but away So that means P will decrease because del P del N is negative, or rather P star, sorry. The piezometric pressure will decrease when one moves in a direction normal to the streamlines, but you're moving towards the local center of curvature. Conversely, if you move in a direction normal to the streamlines but away from the local center of curvature, then P star will increase. So if I go back again to that figure, so consider a fluid particle here, which is at this point at time t. It is moving in this. If the flow is steady, then path lines and streamlines are identical. So this streamline is also the path line of several particles. Okay. So if it is moving in a circular path, so you can think of it as a bend. Okay. So if you go towards the outer side of the bend, the pressure will increase. And if you move towards the inner side of the bend, the piezometric pressure will decrease. So this is due to the centrifugal effect. Now, as we have shown you right in the beginning, the net surface force on a particle due to pressure. Now here, of course, I have not looked at P star, I am simply looking at P. It is minus grad P dV. So in streamline coordinates, I can write it as minus del P del S dV into ES minus del P del N dV into En minus del P del P dV into dV. And similarly, if you want to look at the combined net force due to gravity as well as pressure, then all you have to do is replace P by P star in this equation. And you will get the net force on a particle due to gravity as well as the surface force due to pressure. Okay. Now, so as I said before, we are looking at what you may call the continuum model of fluid flow, where you are saying that the fluid consists of an infinite number of particles. Each point is a particle, and the particles move from point to point. A given point is occupied by a succession of particles. Okay. So surrounding the fluid particle, you have also fluid. So the fluid which surrounds the fluid particle will exert a net surface force in a direction normal to the streamlines, which will be directed towards the local center of curvature, and that is given by minus del P del N. Now, as we have seen, if you look at, if you neglect the gravity effect, then del P del N will be negative. Okay, because of the minus sign here. So minus del P del N will be positive. Okay. So the net surface force on the fluid particle in the direction normal to the streamlines, this will provide the centripetal acceleration. So mass times the centripetal acceleration will be equal to minus rho dV into del P del N. And you can give an alternative V point in terms of pseudo forces. So if you don't like the term centripetal acceleration, then the negative of the centripetal acceleration you can call the centrifugal force. And you can say thus that the centrifugal force is balanced by the net force due to pressure. The centrifugal force is in a direction which is towards the outer side of the bend, and the net force on the fluid particle will be towards the center. It's pointing from the outer side of the bend towards the inner side. Okay. So this gives you an idea. If somebody does an experiment and does flow visualization in an experiment, if you look at the streamline pattern, by looking at the curvature of the streamlines, you can argue on which side the pressure will be higher. Now I come back to this figure that I've shown you yesterday. Now we will look at the Galilean transformation in more detail later on. For the timing, let me say that I'm looking at the streamline picture in a moving reference frame. So this hatched curved line here, this represents a section through the solid vein or lathe or bucket. And these are the relative streamlines. This is a relative stagnation point. So if you look at this red streamline, it is moving initially in a direction parallel to the axis OX. Okay, but then it is moving in a curved path. Okay, and going out. So the bucket itself is curved, and because it's impermeable, it does not allow the fluid to go through. So what it does, it forces the fluid to move in a curved path by providing a constraint. So now you have a look at this curved streamline. You see that as you move from point C towards point B, you're moving towards the outer side of the bend. And then when you're moving from point B to point A, you're moving further away in a direction normal to the streamline. So the pressure will increase. So PA, the pressure at P subscript A, the pressure at A. Yeah, any queries?
सिंगल टेक की मेरे को बेसिक आता है फिजिक्स का बेसिक क्या नहीं है मतलब डबल टेक मतलब अच्छे से आता है अच्छा सिंगल टेक डबल टेक
All right, now I've given you the mathematics behind this prediction. Okay, why the pressure at B is larger than the pressure at C, and why the pressure at A is larger than the pressure at B. It is due to the centrifugal effect. Now, what will be the pressure at point C? Can you tell me? Anybody?
Less than at A. Less than
What is
at
the
A.
pressure at point C?
Atmospheric
Less than-
pressure.
Atmospheric pressure.
Yeah, and it will be less
Then
than
I have already written it down here anyway. Because on this side you have air. Okay. But if I look at a section through the jet, which is here, close to the nozzle, perpendicular to the x-axis, you can say it's a good approximation to say that the pressure at all points here are the same and equal to atmospheric pressure. Because the streamlines are straight lines here. But if I take a section to the jet from C to B to A here, this cross section here, you're going through points where the streamlines have curvature. So although the pressure at the surface is atmospheric pressure, inside will be higher than atmospheric pressure. Okay. So the pressure at points on the wetted surface of the vane or bucket will be larger than atmospheric pressure. See, on the other side of the vane, you have air. It is exposed to the atmosphere. So the pressure on the portions of the solid vane which are open to the atmosphere, the pressure there is P atmospheric. But if you look at the inside surface of the bucket, which is wetted by the liquid, which is water in this case, the pressure will be larger than atmospheric pressure. So the deflection of the water jet will result in an application of a net force on the vane. And if you allow the vane to move, then you're getting work done. And the rate of work done will be the power developed by this blade. Okay. Now, our goal is to predict the power developed by a single blade of the Pelton turbine, and then try and predict what will be the power developed by the entire turbine. Now, as I mentioned before, the simplest way to do it is through balance of linear momentum. And that is what you'll find in most books. But you can also get the same result by applying the first law of thermodynamics. And also, if you wish, you can apply balance of momentum. So there are three ways to analyze this problem. Okay. Now we'll begin with the first method. So we need to know what is the net force on the fluid in the control volume. So what I'll do now is, if you don't have any queries, I'll close this document and open another document. Are there any questions on the material that I've covered so far today? Okay, so I'll close this document. Okay, now let us look at force on a solid surface due to pressure exerted by surrounding fluid. Okay, so we'll consider a point P, capital P, on a solid surface adjacent to a flowing fluid. So I have a little sketch here. So this black surface is the interface between the solid below and the fluid above. And I've shown the unit vector normal to the solid surface at the point P, which is pointing from the solid into the fluid. And we'll consider a small area, an infinitesimally small area surrounding the point P, which I'm calling dA. So if P, small p is the pressure, fluid pressure at the point P, point capital P, then you know the magnitude of the force due to pressure exerted by the fluid on the solid is P into dA. Now what will be the direction of this force? The magnitude of the force is PdA, so pressure units is Newton per meter square, multiplied by meter square, you will get the force dF in newtons.
From
So
fluid to solid.
Will act in the direction of minus n. Why? Anybody? If we look at normal stresses in a fluid, for simplicity, consider a fluid which is at rest. The normal stresses in a fluid at rest, are they tensile or compressive?
Compressive.
Compressive. Okay. Think of it this way. Suppose this fluid is a gas. Then what is producing the pressure? Well, the molecules of the gas are bombarding the solid wall. They'll come at an angle, maybe hit the wall and get reflected. So there's a change in momentum of the molecules. Okay. And that will give rise to a force on the solid. Okay. So that force will always be in a direction which is pointing from the fluid into the solid. So if n is the unit vector, n hat here, pointing from the solid to the fluid, into the fluid, and normal to the surface here, then the force direction will be minus n. So if I say the vector pressure is dF with a subscript PRESS, suppose dF pressure is the net pressure force in vector form exerted by the fluid on this element dA. It will be the magnitude PdA multiplied by minus n. So in other words, we can write dF pressure as minus P into the unit vector N into the magnitude dA. So the left hand side is a vector, right hand side is a vector. You have an infinitesimal quantity here dA, and you have an infinitesimal quantity dF here. Okay. Now this P is the absolute pressure or static pressure, which usually will be positive. Okay. The pressure in a fluid will be positive. Gauge pressure can be plus or minus, but pressure is positive. This is absolute pressure. Now, what is the net force due to pressure on a surface enclosing a region in space? Now, consider a region which I am calling capital R. Now, let the boundary be del R. So, this is a notation which is used by some authors. Sometimes it causes confusion because if you see del, you think it's a small quantity, but here this del R is not a small quantity. The del R simply is a reminder that it is the surface of the region R. Okay. So the net force due to pressure on the surface del R enclosing a region R will be, then we can get it by integrating this dF. Okay. So you will have minus P N dA over del R. Okay. I have taken some examples. Suppose I have a solid with a square cross section which I have shown here in blue. And let us say you have air all around which is at rest. So the pressure is either you can call it P subscript ATM, or here I call it PA for brevity. So I have asked you this question before, what will the net force? And the answer is simple, the net force is 0. So as you can see, if I look at these two vertical faces, the areas are the same. And the pressure force on the left hand side is PA multiplied by the area. It acts from the left to right. And if you look at the right side here, the magnitude is PA times the same area. Okay. And it acts from right to left, because in both cases it's a compressive force. So the net force in the horizontal direction will be 0 because of the cancellation effect. Similarly, in the vertical direction also, because the areas are the same, and this is a distributed force which is uniform with the same magnitude. The force on the top and the force on the bottom, the magnitude are the same and they are in opposite directions. So it's easy to see that the net force is the 0 vector. Now, let's make the problem more complex. So consider a solid with an arbitrary shape and is surrounded by air on all sides, and the air is at rest. So you can say the pressure is constant, the atmospheric pressure P subscript A. So it's a distributed force now. I have shown the arrows here. They are all in the direction normal to the curved surface of the solid. Now, how would you find the net force due to pressure? Now, I asked you this question and I can ask you again today. What do you think will be the value of this net force?
0, 0.
0.
It to be 0. But can you prove it using this relation minus P and dA?
Yes, sir. For every direction of the, as the curve is a continuous function, for every n cap, there will be a minus n cap associated with it. So while we integrate along the boundary, those two cancel each other.
Like the line integration will cancel to 0 straight away. Like along the parameter, along the curve, it will cancel to 0.
Got it.
You can convert the surface integral to a volume integral. So you can write it as minus the volume integral of grad P dV. And if P is a constant, say P naught or P in this case PA, then grad P will be the 0 vector. Then the net force due to a constant pressure will be minus the surface integral over del R, P0 and dA, or grad of P0, which is 0, dV, which is 0. Okay. Now it may not be immediately obvious how to use the Gauss divergence theorem, but it is a simple exercise. Now, have you got accounts in Moodle? In the
Yes,
Institute
sir.
Moodle server?
Yes, sir.
Yeah, I made a request to enroll all of you. So we'll be giving you assignments. So here I've written it as an exercise. The divergence theorem or Gauss's theorem, you can write that in this way. If R is a region of three-dimensional space and the boundary, which I'm calling del R, is a piecewise smooth two-dimensional closed surface, and if P is a continuously differentiable vector field defined in and on the boundary of R, and if N is the unit outward normal at a point on the surface del R, then you can show that the surface integral B dot n dA over the surface enclosing the region is the volume integral of divergence of B dV. So this is something you study in your first year, second semester, vector calculus. Using this, I want you to show that P times Nx dA is del P del x dV. P times Ny is del P del y. And if I assume that A, B, and C are correct, then the vector form of it is P and dA is grad P dV. So if I look at the fourth equation, the vector equation, its x component is equation A, y component is equation B, and z component is equation C. So A, B, and C are three scalar equations, and D is a vector equation. So if you look at the net force on a solid body, okay, you can show that the net force will be 0. Now another way to look at it is, if you look at Nx dA over del R, this will be 0. This you can show into the divergence theorem. So A, B, and C here in the second question are scalar equations, and D is a vector equation. So this 0 here is a 0 vector, which is 0 Ex plus 0 Ey plus 0 Ez. And this vector equation D in part D is equivalent to the three scalar equations in part A, B, and C. Okay. Now, any idea how you use the divergence theorem to do this? You have to think of what is the suitable P which will give you these results. Okay. Anyway, we cannot do everything in the class. Okay. You need to do some things yourself. So I've given you the results. So using the Gauss divergence theorem, you can show that if you have a solid of arbitrary shape and there is a distributed force due to pressure which is uniform on the surface, even if the surface is a curved surface, a complex shape, the net force due to pressure will be 0. Now you might have used this when solving problems in your second year, but this is a second level course, so I expect that you will look at the mathematics and rigorously show that this is 0. Alright, now you know that engineers define a quantity called gauge pressure. This gauge pressure is the difference between the absolute pressure or static pressure and the atmospheric pressure. So gauge pressure can be 0, it can be positive, it can be negative. If gauge pressure is negative, we say...
Excuse me, sir.
Yeah.
Sir, there is background noise. I think two people's Two people are unmuted unintentionally.
Okay. Should I mute all?
Yes, sir. So maybe.
So let us talk about the gauge pressure. Now we can write the absolute pressure then as the sum of the gauge pressure and the atmospheric pressure, which is a constant. So if you want to find the net force due to a pressure distribution P of x, y, z, t acting on a surface, so this is due to fluid surrounding region R. It is given by the surface integral over del R minus of P and dA. Minus because it's a compressive force and N is the outward normal pointing from the solid to the into the fluid. So if I replace P by P gauge plus P atmosphere, then this integral I can write as the sum of two integrals. One involves the gauge pressure and the other involves the atmospheric pressure. Now what will be the value of the second term? Second term will be 0. Okay. So instead of integrating the absolute pressure multiplied by N dA, what you can do is simply take the gauge pressure times N and multiplied by dA. So then you will get the same value. Now this has an advantage. Suppose you consider a case where the distribution of pressure is what is as shown in the on the left. Okay. So it's P atmosphere everywhere except on this arc over here. Okay. If you look at the gauge pressure, it is 0 most of the surfaces except this part. So then, instead of carrying out the area integral over the entire surface, you can simply carry out the area integral over only this part. And you know on the other part the gauge pressure is 0, so it will not contribute to this integral. Okay. So you can take a shortcut when solving problems. So this idea is useful when you apply Reynolds transport theorem and try to estimate forces by making simple approximations. Now let us look at forces on a blade or vane or bucket of a Pelton turbine or Pelton wheel. So I've been talking about this, but I thought it's a good idea to explain things separately. So this is a section through the blade. As you can see on the right hand side, you have the fluid is air. So this red, what I'm showing this line, this is those portions of the bucket which are exposed to the air. The surface of vane or blade exposed to the atmosphere. And the blue surface here, the inside surface, this is a surface which is wetted by the liquid. So I can call it the wetted surface of the vane or blade, which is adjacent to the impinging liquid. Now the pressure on this red portions of the vane is atmospheric pressure. And the pressure due to the liquid here will not be atmospheric pressure. It will be more than atmospheric pressure. So if I show the distribution, force acting on a blade or vane, I have the distributed forces due to P atmosphere. For brevity, I simply call it PA over here. So you have a distributed force which is acting normal to the curved surface on the right over here and on this small thickness. Okay. Now, if you look at the pressure distribution on the inside, it may be larger than atmospheric pressure and is always normal to the surface. Okay. So I have shown arrows whose lengths are larger than the arrows on the right. Okay. And there will be a net force, resisting force, if this bucket is moving at constant velocity. And our goal then is to estimate what is this external force, F subscript B, the force on the blade or the bucket. Okay. One way to do it is if we can find out what is the pressure distribution and carry out the integration. But then that will require solution of Euler's equation. Okay. Now, I've shown you earlier that this is the stagnation point, and the pressure there I'll show you later will be P atmospheric plus rho J times the square of the relative velocity. Okay. So this is the relative stagnation point. Now, when solving the problem, you can choose different control volumes and come up with the same answer. So, convenient control volume, I will show two control volumes. I am calling the first one control volume 1. So, we want to estimate what are the forces acting on the system which occupies the control volume. So, the control volume is indicated by dotted lines. So, we have taken one surface which cuts through the impinging jet, normal to the x direction. So this is the inlet which I am calling 1, and I have taken one surface along the interface between air and the liquid. Okay, this curved surface. Then we have a surface which is cutting through this portion of the jet. So here this is an outlet. So this I am calling 2. And similarly, you have another outlet here, which I am calling 3, and the remaining surface we are calling 4. Not remaining surface, the other outer surface of the plate. And the remaining surface we'll call the total surface minus 1, minus 2, minus 3, minus 4. Now here, the system which is inside the control volume includes the fluid as well as the solid weight. Now the solid also is a continuum, so there's no harm in doing it. And this is already done in most books. But if you want to be very precise and say I am going to apply Reynolds transfer theorem only to the fluid region, then you can take an alternative control volume, which is shown in this figure. I am calling control volume 2. Then I am taking a control volume which includes only the liquid region. Okay. So this surface 4 now is different. It is the wetted surface of the bucket. Okay. So in this case, you have to look at the net force exerted by the solid on the liquid which is inside, and I'm calling this F4 over here. And you have to separately look at the free body diagram of the vane and say that the force exerted by the solid on the liquid on this surface 4 is equal and opposite to the force exerted by the liquid on the solid. So this F4 is the net or resultant force exerted by the pressure distribution which I showed you before. Okay. So then you have this external force on the solid, the net force exerted by the liquid on the wetted surface, and the force due to atmospheric pressure. So this is one way to analyze it. Then you have to look separately at the mechanics of the vane, the solid vane, and the mechanics of the fluid, the liquid separately. Okay. You can get the same result. Of course, here I have not shown the body forces because we are interested in the force in the horizontal direction. And in any case, the volume of liquid is so small that the body force is negligible. In the other case, you can get the answer quickly. It is not that rigorous in the sense that we are going to apply Reynolds transfer theorem to the entire system which includes the solid as well as liquid, and that is not discussed in any of the undergraduate books on fluid mechanics. But you'll get the same answer. The answer will be correct. So as far as this course is concerned, I just want to mention some of the final points, but you may want to get the answer quickly. So this is the control volume which will help you find the answer quickly. Now, what is the net force due to pressure on this surface? So let me show you the forces acting on the fluid or the system inside the control volume. So I've shown the external force in green over here, FB. This is the force which prevents the bucket from accelerating. Okay. Now, you know the distributed force on the right side here. It is a uniform distributed force. The force per unit area is PA. Now, if you cut through the liquid at the outlet here, section 3, and the outlet here, section 2, here the streamlines are all straight lines. Okay. So when the streamlines are straight lines, because the cross-sectional area of the jet is very small and the liquid jet is surrounded by air on all sides, which means that the pressure on the surface of the jet, free surface of the jet, which is the interface between the liquid jet and the air, is atmospheric pressure. You can say that it's a good approximation to say that at all points inside this section, inside the liquid, the pressure is atmospheric. And of course, on this side also, because you have air, it is atmospheric pressure, it will all act normal to the surface. Okay. And again, if you look at the inlet section, the streamlines are parallel. So at points on section, which I call section 1, okay, at all points in the liquid at section 1, we'll say the pressure is atmospheric pressure. Okay. But if I take a section, say in this direction, from this point to the bucket, okay, where at different points on the section you see the streamlines have curvature, then you cannot say the pressure is atmospheric pressure. It will be larger than atmospheric pressure, and I've gone to great depths to explain why by looking at Euler's equations of motion in the normal direction. Okay. So it's not that everywhere in the liquid jet, if you take a section through any point through the jet, the pressure is atmospheric pressure. It will be so if the streamlines crossing that section are straight lines. So here at section 1, the streamlines are all horizontal and parallel to the x-axis, roughly. Okay. And at section 2, when it's coming out, the streamlines are inclined, but they're all straight lines. Okay, the curvature is in the vicinity of the splitter plate over here. Okay, where the bucket is curved. Okay, and similarly at section 3, when the fluid is coming out of the control volume here, if you look at the streamlines, they are inclined to the x-axis and y-axis, but they will be straight lines. So that is the first concept. That is estimation of the pressure at points inside the liquid jet where the streamlines to those points are straight lines. You can say it is atmospheric pressure. So now what is the net force on this complicated shaped control volume due to pressure?
Zero.
Zero. Again, I have shown it to you using the Gauss divergence theorem. Okay. So the net force due to pressure will be 0. And there is an external force. So what we have to do next is look at the change in momentum of the fluid. So momentum in and the momentum out. Okay. But then there will be an unsteady term in your Reynolds transport theorem. If you do the analysis using a reference frame which is stationary. What we'll show in the next class that if you make a Galilean transformation to a translating frame of reference moving with constant velocity, that is another inertial frame, so you can apply Newton's laws of motion in that reference frame, but then you have to use the relative velocities, the velocities as seen by an observer fixed to that frame. We will show that the flow will be steady in that moving frame. So you don't have to look at the unsteady term. So that requires derivation of Reynolds transport theorem for translating control volumes. Now you might have solved problems using translating control volumes in your second year course. Am I right?
Yes, sir. If you're translating, yeah.
You have. Okay.
Hmm.
So the result is known to you, but perhaps you have not looked at the details. Okay. So if you look at Fox and McDonald, he has problems, but he simply says the flow is steady in the moving frame without explaining what it means precisely. Okay. So we'll find the difference, find the Eulerian derivative del T in the moving frame as well as the stationary frame, and show you the relation between the two using a Galilean transformation. And then we can explain why the flow is unsteady in one frame and steady in the other frame. Okay. If you don't go through all this analysis, then there's nothing in this course. Ultimately, there'll be some simple formula. Okay. But we are studying in IIT. We want to explain everything. We teach engineering as a science. So that is why we have to go through all this mathematical details.
Sir,
Yeah.
sir, are you going to send the notes regarding that Galilean transformation or the Bernoulli or the streamlines from a reference frame?
Yeah, sure. But see, I'm typing in all the details is taking time. Okay. I want to remove all the errors before I send it to you. Okay. So the Galilean transformation part, that is not, all the details have not been typed in. Okay. So this, by the way, I've already uploaded 4 files. Have you seen that? Are you able to download the files?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So I've just uploaded 4 files. Is the format preserved when you download it?
Yes, sir.
Okay. So give me some more time. I'll definitely upload all the material. Okay. And then if you have queries, we can come back and discuss. In this format, one of the advantages is we can go back to things that have already been covered because it's already typed in. Okay. The disadvantage is that you're not seeing the equations come up before your eyes. You're seeing everything at one shot. Okay. But one advantage is that I'm giving you all the material. It's not that you're relying on your own class notes or the class notes of your friend. Okay. Now, which control volume are you more familiar with? This control volume 2 or control volume 1?
One, like the pressure
Control volume
distribution
1.
in control volume 2 will be complicated.
Okay. But you may wonder why you're getting the same result. Because Euler's transport theorem, the way you have studied it in your second year, that is applied only to the fluid region. Okay. So if you want to see the relation, then you have to look at control volume 2 and apply Reynolds transport theorem only to this control volume. Okay. And say the net force exerted by the solid weight on the fluid is simply what we are calling F4. And this F4 is like action and reaction. So the action of the solid on the liquid is equal to the reaction of the liquid on the solid. So this force, if it acts to the left, will be equal to the force exerted by the liquid on the vane in magnitude but in opposite direction. Okay. And then if the vane is not accelerating, then the net force is 0. Okay. So the net resultant of F4 vector and FB vector and the remaining force due to the atmospheric pressure, they will add up to 0. That makes it more complicated. Okay. And then you have to come back over here and look at the force due to pressure on part of the control volume here. So what you have to do, you have to add and subtract things. And then ultimately you will come up to a something which is equivalent to this. Okay, and you can show that the net force due to pressure will cancel out. So anyway, for the time being, let us focus on simple things. We'll look at control volume 1. So we have shown rigorously that the net force due to the pressure on the bucket here will be 0. But what are the assumptions here? The assumptions you have made is that at the inlet section 1, at the outlet section 2, and at the outlet section 3, the pressure at points where your particles are liquid and not air, there also the pressure is atmospheric pressure. So you must understand the justification. There are two reasons behind this. One is you have a circular jet, and at all points on the free surface of the jet, which is the interface between the liquid and the air, the pressure is atmospheric pressure. You can neglect surface tension effects. So if we take a point which is just inside the liquid jet surface, pressure will be atmospheric pressure. Okay. The radius of curvature is very small, so surface tension is negligible here. Okay. But if you look at, say, points on section 1 and look at the streamlines on those points, those streamlines also have to be straight lines, roughly, for the pressure variation in the normal direction to the direction normal to the streamlines to be negligible. If you take a section somewhere here where the streamlines are curved, then there will be a pressure variation in the normal direction. So a pressure on the free surface is atmospheric pressure, but at points inside it may not be atmospheric pressure. Now what I'll do is, again, are there any questions regarding this?
Sir, so in solution of the Euler's equation, surface tension will come up as boundary conditions, is it?
Yeah, if you want to be a stickler for rules, you can look at the surface tension effect also. Okay, so if you look at the surface of the jet, on the outer surface, the pressure is atmospheric pressure. If you take a point which is just inside the liquid liquid air interface, the pressure will differ from atmospheric pressure by a very, very small amount due to surface tension.
Yes, sir, but like in this case it's clear, but like generally I'm asking, like in a general
situation, in general there will be a surface tension, of course. Yeah.
And that will be used as a boundary condition for solution of Euler's equation.
Right. But
Okay.
see, the atmospheric pressure in SI units is of the order of 10 to the power 5 Newton per meter square. Okay.
Yes.
And do you know what is the surface tension for? Of course, surface tension in this case for the liquid, which is air, water, it depends on temperature. But do you know? Can you give me a ballpark number? What is the surface tension?
No, sir, no.
40 millinewtons.
May not be 40. It is 0.0728, something like that. Newton per meter.
Yeah, so 72.
72 millinewton. It is millinewton, and the other one is 0.1 megapascal. Okay.
Yes, sir.
So this is 0.0728 multiplied by divided by the radius of curvature. Okay.
Yes, sir.
Okay. So it is a small quantity. We are
Yes,
making
sir.
many approximations. Okay.
Yes, sir.
All right. Now, see, if you look at the pressure variation in the direction normal to the streamlines, it is rho v square by r. Okay. R is the local radius of curvature. Suppose the streamline is a straight line. What is r?
Infinity.
Infinity. So 1 upon r is 0. Okay. So the variation of pressure in the direction normal to the streamlines due to the centrifugal effect is not there when the streamlines are straight. So we have chosen a control volume where at portions where the fluid is entering or leaving the control volume, the streamlines are straight lines. Okay. So the centrifugal effect is negligible. surface tension effect anyway is negligible. Okay, and all around the surface you have pressure, which is atmospheric pressure. Of course, there is a gravity effect. Okay, so because of the gravity effect, this water jet actually will not be horizontal. It will deflect downwards like a projectile. But then the deflection, the vertical distance through which it comes out will be very, very small because this jet velocity is usually very large. It may be of the order of 100 to 150 meters per second. Okay. So the gravity effect also is negligible here.
Yes.
I can take it to be the atmospheric pressure. So this is an approximation, and we have shown rigorously that if at all points on a complex closed surface the pressure distribution is uniform, the net force is zero. So good news is that you don't have to worry about how to find the net force due to pressure. So there will just be a change of the momentum of the fluid, okay, and the external force. But when you find the change in the momentum of the fluid, if you use a reference frame which is stationary, then you have to account for the unsteady term. All right, any more questions? If not, then I'll stop here today and we'll resume at 11 o'clock next Monday. In the meantime, I'll try to upload an assignment for you in Moodle.
Sir,
I don't know whether your accounts in Moodle have been created. Okay, I have requested the Moodle help desk, so I have not yet checked.
sir,
Okay. Yeah.
sir, here there are places near the entry and the exit where the streamlines are parallel, right?
Yeah.
So,
Approximately parallel.
yeah. So if we go to the discussion at the beginning of the class where you were using a frame like E, S, En, and EB.
Yeah.
So in that case, the normal direction, there was a normal direction and an instantaneous radius of curvature. So,
Right. So
you were doing, and there was a term of del P star and del N.
right. Right.
So here, for the case of a parallel streamline, so the curvature is infinity. So there won't be any drop in pressure.
No, curvature is not infinity. Radius of curvature is infinity.
I mean, sorry, the radius of curvature. Yeah.
Yeah. So curvature is zero. So del P del N is zero. Of course, you can say what is En. En is not defined actually. Okay. If you want to define it as del S of Es. Okay. So the definition of En as del S of Es divided by its magnitude, that is no longer valid in the limit. Okay. But you can always define a normal direction. You have two choices. It can either be pointing in one direction or in the opposite direction. Okay. You can always define two normal directions.
So what will be the pressure variation?
Pressure variation in that direction, the variation of piezometric pressure will be zero. Variation of piezometric pressure will be zero. Now, piezometric pressure has two components, the static pressure component and the gravity component. Okay. Now, if you look at the gravity component, that variation is small because of the length scales involved. See, in fluid statics, okay, how does, if you look at 2 points, what is the difference in pressure? Suppose you have a liquid which is at rest. Consider 2 points 1 and 2. What is the difference between P1 and P2?
Rho gauge, like under
It
gravity.
depends on the vertical
Otherwise,
distance
zero.
between the 2 points, right? Suppose 1 and 2 are both on the horizontal plane, on a horizontal plane, then P1 will be equal to P2. Okay. So if you say that h is the vertical distance between 0.1 and 0.2. Okay. Then what is the pressure difference between those two? It is simply rho GH, right? Now use SI units. Density of water is 1000 kg per meter cube. Let us say gravity acceleration due to gravity is 10 meter per second square. Okay. So you have 1000 multiplied by 10, so that is 10 to the power 4. Okay. But this height, suppose this height difference is of the order of 10 millimeters, let us say 1 centimeter. Okay. 1 centimeter will be 10 to the power minus 2 meters. Then that is 10 to the power 4 into 10 to the power minus 2, so that is 100. Okay. So delta P may be 100 Newton per meter square, but the atmospheric pressure itself is 10 to the power 5 Newton per meter square. So the variation in pressure, if you look at it, is relative variation. It is 10 to the power 2 by 10 to the power 5, which is 10 to the power minus 3. Is it clear?
Yes, sir.
All right. So when the height difference is small, okay, the difference of pressure due to the gravity effect is small and can be neglected compared to PA.
So the gradient of that P star with the N here in this case will be 0 at this close vicinity.
Gradient of P star with N will be 0 if the streamlines are straight lines.
Okay.
Okay, because we are not considering viscous effects. It's an inviscid fluid.
So on
We are not
later
able
on,
to quantify the viscous effect here.
so later onward, as we move farther away, as they cease to be parallel, at that time it will become less than 0.
Yeah. So if viscous effects are not there, and there's no acceleration in the direction normal to the streamlines, okay, then the sum of the body force and the pressure force is 0. And that is reflected in the statement that del del n of P star is 0. So if I say del del n of P star is 0, what I'm saying is that the acceleration of the fluid particle in the normal direction is 0. The viscous force in the normal direction is negligible. And you have a balance between the pressure force and the gravity force. But if the gravity force is also negligible, then the pressure is constant. Ultimately, it boils down to that. So one way of looking at it this way is that instead of separately looking at the gravity force, we can forget about the gravity force and look at the piezometric pressure. Okay. Now then you will have a piezometric pressure using the liquid as well as the air. Okay. And then in the air, you can say the piezometric pressure and the absolute pressure is the same. Why? Because the density of air is very small. The density of air will be 1 upon 1000 times the density of the liquid. So in a simple minded analysis, you can say that the gravity effect is negligible because the volume of the liquid here is very, very small. And look at the difference in heights between 2 points on the inlet section and 2 points on the outlet section. They're very, very small. Okay. And you can also look at the case of a vertical Pelton turbine where the shaft is vertical. In that case, this entire diagram is in the one single horizontal plane. If you have a Pelton turbine with a horizontal shaft, then this y direction is the gravity direction. Okay, but in the case of a Pelton turbine with a vertical shaft, the gravity vector will be in the z direction, normal to the plane of the figure. In that case, you don't have to worry at all about the gravitational effect. Any other queries? All right, then let us close the meeting.